Okay, picture this for a second. You're trying to navigate a sprawling, totally unfamiliar neighborhood. Or maybe you're trying to plan a massive cross country road trip, but you have to do it entirely from memory. No GPS on your phone, no paper maps, literally no tools at all. It would be absolute chaos, right? Well, welcome to this explainer. Today, we're going to unpack the incredible, fascinating tools that humans have developed over centuries to understand and ultimately navigate our planet. So, here is the fundamental problem that has tested brilliant minds for centuries. How exactly do we capture this massive, highly textured, three-dimensional sphere we live on and accurately translate it onto a simple, flat piece of paper? Okay, let's dive into this and see exactly how cartographers managed to solve this monumental problem. Here is our quick roadmap for the explainer. We'll start with 1. Maps versus globes, then move to 2. Exploring types of maps. After that, we'll look at 3. Sketches versus precise plans, then 4. Drawing complex geographical features, and finally, 5. The pioneers of cartography. All right, jumping right in. Section 1. Maps versus globes. Because building our geographic understanding really starts with choosing the right broad-scale tool. The two absolute heavy hitters at our disposal are the map and the globe. Now, a map is simply a drawing of the whole Earth, or maybe just a tiny part of it, rendered on a flat surface. A globe, on the other hand, is an accurate, three-dimensional, spherical representation of the Earth. The massive distinction here that you need to keep in mind is that flat surface versus the true spherical shape. Now, what's really interesting about this comparison is the real-world trade-off between everyday practicality and absolute perfect accuracy. Maps are incredibly easy to fold up and carry around, making them super practical for us. And they use great signs and symbols to convey tons of info. But because you literally can't perfectly flatten a sphere without stretching something, they always contain a little bit of distortion. Globes are the ultimate truth. They represent the true curved surface perfectly. But let's be real, they are bulky, difficult to carry, and they just can't zoom in enough to show the minute details of your local street. Moving on to Section 2, exploring types of maps. Because once we do decide to flatten the Earth, we have to decide exactly what details we want to show. Honestly, maps are a total game changer for human civilization. We use them for literally everything, from teaching students in a classroom to helping engineers with complex town planning. They're essential for navigation and wonderfully portable when you're traveling. But you know what their real superpower is? Communication. They rely on standardized signs, symbols, and colors. This presents complex information clearly and concisely, leaving almost zero room for misinterpretation. So, depending on what you need to know, you grab a specific type of map. Take political maps, for example. These are entirely focused on human-made divisions. They're the ones showing you the invisible boundaries of countries and states and pinpointing the exact locations of capital cities and important towns. But if you want to look at nature, physical maps provide an amazing alternative. Instead of human borders, they use different colors to highlight the natural world, your mountains, plains, valleys, and rivers. And this brilliantly illustrates how cartographers capture local landforms. Topographical maps even take it a step further. They're built on highly accurate land surveys to give detailed information about local streams, roads, and buildings, making them absolutely essential tools for civil engineers and the military. Now, regardless of the type, every single map relies on the concept of scale, which honestly can feel a little counterintuitive at first. A small-scale map actually shows a massive land area squeezed into a tiny space, like, say, 1 centimeter representing 200 kilometers. Because of that extreme squeeze, features aren't clearly visible, it lacks fine detail. Conversely, a large-scale map shows a much smaller land area taking up a bigger space on the paper, like 1 centimeter representing just 1 kilometer. This is what allows for highly detailed information about local, everyday features. Which brings us nicely to Section 3, sketches versus precise plans. Let's shift our focus from those wide regional maps right down to the hyper-local level of navigating our immediate surroundings. Think about the stark visual difference between doodling directions on a napkin versus looking at a true blueprint. A sketch is just a rough, memory-based drawing. It only shows a few chosen landmarks to help someone quickly find their way to a specific spot. A precise plan, however, is rigid, meticulously measured, and drawn perfectly to scale. So the crucial point is knowing exactly when to use which. You use a sketch when you just need to give someone a general vibe or sense of a location. It's rough, completely unscaled, and generally lacks fine details. But you use a plan when you need a perfectly scaled horizontal cross-section of a small area, like a school's layout, where the distance between two walls must be flawlessly accurate. Okay, Section 4, Drawing Complex Geographical Features. How on earth do we depict massive 3D natural phenomena on a totally flat piece of paper? Well, geographers use specific, specialized diagrams to make this happen. Imagine the thick layers of the Earth's crust undergoing intense compression over millions of years. They literally fold. The arches, or the upward folds, are called anticlines, and the troughs, or the downward dips of those folds, are known as synclines. But what happens when the crust doesn't just neatly fold but actually breaks? Well, strain and tension can cause deep faults or fractures. When these massive cracks occur, the surface between them can actually sink downward. This displacement leaves the adjacent upright blocks standing high above the newly sunken valleys, creating what we call block mountains. Well, let's move to dynamic systems and see how this builds. These exact same concepts apply beautifully to things like rivers. Through diagrams, we can trace a river's entire life cycle. We can spot its origins way up at the source on high ground, follow it as it twists and widens through its middle stages, all the way down to where it fans out and meets the sea at its lowest stage. But to really read these river diagrams, you gotta have the precise vocabulary. A tributary is a smaller stream that drains right into the main river, adding water to it. A distributary is the exact opposite. It's a channel that splits away from the main river and doesn't ever rejoin it. A meander is that classic loop-like bend the river takes as it flows. And finally, the delta is that incredible fan-shaped feature at the river's mouth, created by years of deposited silt. All right, bringing it home with Section 5, the pioneers of cartography. Let's look at the historical context and the brilliant minds that built these tools. But first, a quick piece of energetic trivia for you. Have you ever wondered where the word map actually comes from? The science and art of map making is called cartography, and it's derived from two French words, carte, which means map or card, and graphie, meaning representation or description. The historical institutions that practice cartography are just monumental. Take the Survey of India, or the SOI. Established way back in 1767, it's actually the oldest scientific department of the Government of India. Operating under the Department of Science and Technology, this is the national organization tasked with the incredibly massive job of scientifically mapping the entire country and officially demarcating its external boundaries. And you simply cannot talk about the history of mapping India without mentioning James Rennell. A brilliant British geographer and surveyor, he's widely known as the father of Indian geography. His extensive surveys, particularly in the Bengal region, resulted in some of the very first truly accurate representations of the area's rivers and coastlines. His seminal work, The Memoir of a Map of Hindustan, published in 1788, was an absolute game-changer for regional cartography. Wow, we've covered a ton of ground today. We went from translating a 3D planet onto flat paper, to understanding the visual language of rivers and tectonic plates, right through to the early pioneers of mapmaking. So the next time you need to find your way, ask yourself, from rough memory sketches to precise 3D globes, which tool in the geographer's toolbox will you use next to understand your place in the world? Thanks so much for joining me on this explainer, and keep exploring.